The theory of moon landing is that the fact that humans land on the moon is a fictional story. One of the main arguments of this theory is that the moon landing was actually made out of false images produced by NASA. According to this, the moon landing didn't really happen, but the US made a fake video to counter the Soviet Union and released it to the world. But this is a groundless claim, and evidence of the moon landing has been verified in several ways. For example, the reason I can't hear the lander falling during the moon landing scene is because the moon's atmosphere is very thin. Also, physical data measured on the surface of the moon and samples collected during the lunar landing mission are among the evidence. Therefore, the theory of moon landing Gullah is not true, which is a fictional theory based on misunderstandings and speculations. The escape speed of the moon is about 2.38 kilometers per second. This is the speed at which the moon's gravity no longer holds objects and escapes, much lower than the Earth's escape speed. This escape velocity is determined by the moon's mass and radius, and if the rocket is accelerated at a speed sufficient to exceed the escape velocity, it can leave the moon and return to Earth. For this reason, the lunar probe accelerates at sufficient speed on the moon's surface, overcoming the moon's gravity and returning to Earth. The lunar lander will fly around the moon with a rocket launched from Earth and then land slowly using the moon's gravity. At this point, the rocket must be accelerated to sufficient speed to overcome the moon's gravity. To do this, the rocket gains speed beyond the escape speed, a speed that is sufficiently fueled and accelerated before the Earth's departure. And it's continuously accelerating to get out of the Earth and fly to the moon. For this acceleration, the rocket engine is divided into several stages, and while approaching the moon, it operates the rocket engine to control its speed. After landing on the moon, the rocket is activated again, leaving the moon and returning to Earth. At this point, the rocket will continue to accelerate with sufficient fuel and return to Earth at a speed that exceeds the escape speed. The moon has a very thin atmosphere. However, the density of this atmosphere is about 1/billionth of the Earth's atmosphere, and it can be said to be almost non-existent. The moon's atmosphere is mostly composed of elements such as helium, neon, hydrogen, and argon, and is very different from Earth. Also, the moon has little magnetic field, so it is not protected from solar wind and radiation from celestial bodies. For this reason, the moon's atmosphere is very weak and has little effect on the human body. However, there are elements such as hydrogen and helium on the moon, which are not removed by the solar wind that occurs on the moon's surface, but are responsible for slightly reducing the moon's weight. Also, these atmospheric elements help study mineral resources on the moon. That's right. There's very little frictional force on a spacecraft landing on the moon. This is because the moon's atmosphere is so thin that there is little air resistance. Therefore, when a spacecraft falls to the surface of the moon, friction caused by mechanical contact or irregularities in the terrain acts on the spacecraft. However, as the spacecraft lands on the moon's surface, the gravity of the moon acts as a force that pulls the spacecraft to the moon's surface. Therefore, lunar landers must have sufficient momentum and stability to overcome this gravity. Landing on the moon and landing on Mars have different challenges. Moon landings have a very low gravitational pull of about 1/6 of the Earth's, so the amount of fuel needed to land on the moon is minimal. Also, as mentioned above, there is little atmosphere on the moon, so there is little air resistance or friction when landing, making it relatively easy to land the spacecraft stably. Mars landings, on the other hand, are much stronger than the moon at about 1/3 of the gravity of the planet compared to Earth. Also, Mars has a slightly denser atmosphere. Therefore, when landing on Mars, more thrust and stability are required than on the moon, and when landing, atmospheric resistance and friction are present, making it relatively difficult to land stably. Therefore, the landing of the two planets has different challenges, and the design and operation of the lander require a lot of consideration. There is a possibility that the crew will be exposed to space radiation. Because the Earth's atmosphere protects spacecraft from radiation, unlike Earth, there is a very high level of radiation in space. These radiation exists in various forms, such as electromagnetic waves and particulate components, and the Earth's radiation protection measures are also introduced inside the spacecraft to protect its crew. Inside the spacecraft, radiation protection devices are installed to block radiation. Also, the structure of the spacecraft itself has a radiation blocking effect. These radiation protection devices play an important role in the crew's survival in space. However, for crew members living in space for a long time, long-term exposure to radiation is likely to cause health problems. Therefore, spacecraft such as the International Space Station monitor crew health and take radiation protection measures if necessary. Spacesuits can play a role in reducing radiation exposure in part. Generally, spacesuits are multi-layered, and radiation pads or elastic bodies are used inside. These structures are designed to protect the crew's body from radiation. Also, spacesuits themselves may have radiation protection. For example, American spacesuits are made of metal such as aluminum, which has a radioactive barrier effect. These radiation blocking effects protect the crew's body. However, spacesuits do not have a perfect radiation blocking. Therefore, even if a flight attendant is wearing a spacesuit, there is a possibility of exposure to a certain amount of radiation. Therefore, crew members need to take thorough measures for radiation management, such as receiving medical checkups every certain period. I'm afraid not. The lunar lander is designed separately for lunar landings and does not have a rocket engine for return. The lunar lander has the rocket engine it needs to land on, so it lands on the moon's surface using its gravity and friction. The lunar lander then performs missions on the moon's surface, and is not equipped with a rocket engine for the return. Therefore, if the moon's orbiting rocket is docked and returned to Earth, the lunar lander will remain on the moon's surface. The orbiting rocket has a rocket engine for return, so it can return to Earth. In the case of Apollo 11, it consisted of a lunar lander and a return module. The lunar lander landed on the lunar surface to carry out its mission, and the return module remained in lunar orbit. 2 of the 3 astronauts, Armstrong, Oswin and Collins, landed on the lunar surface and performed the mission, while Collins waited in lunar orbit in the return module. After the mission was completed, the 2 astronauts connected to the return module and prepared for the return. The return module used a rocket engine to leave the lunar orbit and head for Earth. The return module is separated before entering Earth's atmosphere, and is finally designed to allow crews to safely land on the ground using parachutes. Therefore, Armstrong returned to Earth with a return module. Apollo 11's return module orbits the moon and waits until it enters the atmosphere before returning to Earth using a rocket engine. Apollo 11's return module began orbiting the moon after being separated from the lunar lander. Then, they waited until they entered the atmosphere without leaving the lunar orbit, and then returned to Earth using the rocket engine again. The return module was not docked with the lunar lander and was detached from lunar orbit to return to Earth. Apollo 11's return module orbits the moon and waits until it enters the atmosphere before returning to Earth using a rocket engine. Apollo 11's return module began orbiting the moon after being separated from the lunar lander. Then, they waited until they entered the atmosphere without leaving the lunar orbit, and then returned to Earth using the rocket engine again. The return module was not docked with the lunar lander and was detached from lunar orbit to return to Earth. The speed of Apollo 11's return module when it left the moon was about 1.5 kilometers per second. That's about as fast as the moon orbits the Earth. The moon's orbital period is about 27.3 days around the Earth. Therefore, it takes about 27.3 days for the return module to circle the moon, which may vary depending on the state of the moon as viewed from Earth. However, since the return module uses a rocket engine to leave the moon directly, it moves at a much higher speed than the moon's orbital speed. On Apollo 11's return, the first lander left the moon and entered Earth's orbit. The return module then burned the propellant left by the lander, entered the lunar orbit with its own engine, and docked with the lander. Later, in the process of returning from the moon to Earth, the return module was used to return directly to Earth, rather than the lander returning to Earth before the return module. Therefore, you might think that the return module was ahead of the lander. Yes, that's right. To dock with the lander, the return module had to align its orbit considering the moon's gravity and speed. Therefore, the return module had to move at a speed similar to that of the lander in order to dock with the lander. To this end, the return module accelerated using propellants while entering lunar orbit, and the lander accelerated at the same constant speed for docking. Therefore, it is assumed that the relative speed of the return module and the lander during docking was not significant. That's right, there's no atmosphere on the moon, so it's impossible to accelerate using a jet engine. Therefore, it must be accelerated using a rocket propellant or chemical propellant. However, gravity is weaker on the moon than on Earth, so it is relatively easy to accelerate using rocket propellants. It is also relatively easier to accelerate from the surface of the moon using rocket propellants, as the surface of the moon has less frictional force than the space within the Earth's atmosphere. But accelerating using rocket propellants is still a very difficult task, requiring high technology and safety measures. Also, the efficient use of fuel is important because using rocket propellants consumes fuel very quickly.